So in this video we're going to give another example of estimating area under the curve, and in this particular example we're going to be working with right endpoints and the need to adjust the bounds of summation. So estimate the area under the curve. We have the curve f of x equals x squared plus x minus 4. We want to estimate the area between the graph of f of x and the x-axis between x equal 2 and x equal 4 using 4 rectangles and right endpoints. So from x equal 2 to x equal 4, what we're being asked to is estimate the area under the curve, which is this area in here. So the first thing to remember is that if we're working over with a closed interval from A to B, and we know we have n rectangles, then we can calculate the width of each rectangle, which we call delta x, by taking the length of this interval, which is going to be b minus a, and then we find the width of each rectangle by dividing it into n pieces. So in this particular case, because it says we want to work and find the area, or estimate, the area under the curve between 2 and 4, we know we're working over the closed interval from A to B. That's equal to the closed interval from 2 to 4. So the first thing is to determine the width of the 4 rectangles that we're going to be using to estimate that area. So the width, delta x, is just going to be equal to the length of the line segment between 4 and 2. So that's the distance 4 minus 2. And then we divide by the number of rectangles. There's going to be 4 rectangles, so 4 minus 2 over 4 is 2/4, which reduces to 1/2. So that's step number 1. Step number 2 is to look at the interval over which you're working and kind of reimagine or reconceptualize this interval in terms of the denominator that's involved in describing the width of each rectangle. So I want to recognize that the closed interval from 2 to 4 is the same as the closed interval of 4/2 to 8/2. So I rewrite the 2 and the 4 in terms of the denominator 2 that I'm going to be using for delta x, the widths of my rectangles. And then I want to go in on the x-axis, and over the interval from 4/2 to 8/2, I want to put in the tick marks that I need to construct my 4 rectangles. So I'm going to start at 2, which is the beginning of the closed interval, and I'm going to rewrite the 2 as 4/2, and I'm going to go all the way over to 4, which I'm going to rewrite as 8/2. And so I want to recognize that between 2 and 4, to get 4 rectangles, I'm going to need to break this up into 4 equally spaced chunks. And then the tick marks on these I'm going to get by starting at the 4/2 and then adding 1/2 to it, the width of the rectangle, to get to the next point on the x-axis. So 4/2 plus 1/2 is 5/2. A distance of 1/2 over, I get 5/2 plus 1/2 is 6/2, or 3. And then 6/2 plus 1/2 is 7/2, and then 7/2 plus 1/2 brings me over to 8/2. And again, because I'm going to be using summation notation like we did in the previous 2 videos, I'm not going to simplify any of these fractions into simplest form, because the form with the common denominator is going to be the one that I need for summation notation. So now I've got my tick marks in, and notice those tick marks are breaking me into 4 distinct regions, which are going to correspond to the 4 rectangles I'm going to build. And each of those 4 regions has width 1/2. Those are the bases of the rectangles I'm going to build. And then it says use right endpoints. So to use right endpoints, what I do is I go to the interval. I go to the start of the interval. If I were using left endpoints, I would start on the curve right above the left endpoint. But because it says to use right endpoints, I'm going to step over from the first number on the closed interval. I'm going to step over 1 space to the 5/2, and from there I'm going to go up to the curve. I'm going to draw the point on the curve, and then I'm going to move back towards that first left endpoint and then draw that rectangle down. And there's my first of 4 rectangles. Then from my 5/2 I go over to the 6/2. I draw the straight line up to the curve. I'm going to want that point on the curve. From there I draw to the left and down to the previous point to make my second rectangle. So I've now constructed 1, 2 rectangles. Now from the 6 halves I go to 7 halves. I draw a line up, straight up to the curve. I want that point on the curve. I draw over to the left and down to the previous point, making my third of 4 rectangles. And now I move over to the far right endpoint. I'm making right endpoints. So I'm going to land on the far right endpoint of the closed interval. Again, we draw from there straight up to the curve. If I were on paper, I would use a ruler. I want that point. I draw to the left horizontally until I'm above the previous point, and I draw down to make rectangle number 4. And I'm going to take the sum of the areas of these 4 rectangles to estimate the area under the curve. And I just want to notice that each rectangle is actually above the curve. So each rectangle contains a little bit of area that isn't under the curve. So my estimate, I didn't want that to happen. My estimate for the area under the curve is actually going to be, I hate it when I do that. It's actually going to be a little bit of an overestimate, and that's okay. It's just an estimate. For these points that I'm using to construct, so each point lands on the upper right corner of the rectangle. That's what makes these right endpoints. And for each of these, I'm going to need to know the ordered pair that goes with it, because I need to know the height of the function at that point, because the height of the function at that point will tell me the height of the rectangle. So here, when I input 5 halves for this point, I know that the output is f of 5 halves. At this point right here, I know when I input 6 halves, the function output is f of 6 halves, and that will be the height of this rectangle. At this point, when I input the 7 halves to get the ordered pair, I input that 7 halves into the function. F of 7 halves will be the height of rectangle 3. That's a horrible arrow. I can't even draw an arrow today. And here, when I input 8 halves into the function, I get f of 8 halves. So this ordered pair right here, this number gives me the height of the 4th rectangle. So I need to add up the areas of the rectangle. I have area of rectangle 1, area of rectangle 2, area of rectangle 3, and the area of rectangle 4. So I'm going to estimate the area under the curve by approximating it with the area of the rectangle. So I need to take area of rectangle 1 plus area rectangle 2 plus area rectangle 3 plus area rectangle 4 and add them all up. But the area of rectangle 1 is just the height of the rectangle, which is the function evaluated at 5 halves. So the height of the rectangle, the function evaluated at 5 halves, times the width. But the width of each of the rectangles is a half. That's my delta x calculation over here. So it's times a half, plus f of the height of the next rectangle is f evaluated at 6 halves, times a half, plus the area of rectangle 3 is going to be the height of rectangle 3, which is just f of 7 halves, times the width, which is a half, plus the height of the last rectangle is f of 8 halves, times the width of that rectangle is 1 half. And when I look at this, what I want to recognize is I can rewrite this using sigma notation. The only number changing in each of the 4 terms corresponding to the areas of the 4 rectangles is the numerator in the function input. And I'm starting at 5. I'm incrementing by 1 until I get to 8. So I can rewrite this as the sum from I equal 1 to 8 of the function evaluated at I over 2. So we are going to increment I until, and it's not going to be from 1 to 8. The first number is a 5. It's going from 5 to 8. 5, 6, 7, 8, incrementing by 1s, and this is times a half. And once we get it to this place right here, where we're saying, hey, the area is approximated by this summation. Now I don't need the picture anymore. The picture's done its job, which was to set up the approximated area calculation, and now I just have a summation from a previous homework assignment, and I can calculate this using the summation formulae that we developed in a previous homework assignment. So I'm going to take this guy right here in the box and move him over to the next slide so that I have some space to work, and say once I get the sum from y equal 1 to 8 of f of I over 2 times a half, I'm going to use my summation formulas to calculate the sum. The first thing that I need to know, there's two big things for my first step I need to notice. One, here's a multiplication by a constant, so a constant can be factored out of a summation. The second thing I want to recognize is that my summation shortcut formulas required that the lower bound of summation start at 1. Here I'm starting at 5, so I have to rewrite my summation to start at I equal to 1 if I want to use the summation formulas. So here I want to change the 5 to a 1, so I decrease 5 by 4 to get to 1. 5 minus 4 is 1, so I'm going to decrease 8 by the same amount. 8 minus 4 is 4, so the distance between 4 and 1, 4 minus 1 is 3, corresponds to the distance between 8 and 5. 8 minus 5 is 3. So I'm still going to be covering the same number of rectangles. And then I factored the 1/2 out, so I just need to take my function I over 2 and adjust the I to start at this new lower bound of summation. Here I want to notice I decreased 5 by 4 units to get to the 1. So to undo that, I need to increase I by 4 units. And as per previous videos, the check on your work is to take your new lower bound of summation and plug it in. So if we plug 1 in, we get 1 plus 4 is 5. And when we plug in the lower bound of summation, I should get back the original lower bound of summation. If I plug in my new upper bound of summation, when I plug it in, 4 plus 4 is 8. I should get my old upper bound of summation. If I don't get that, then I've made a mistake. So once I get it to here, I recognize I now have a summation starting at 1. So I'm just going to rewrite the summation symbol. I'm going to take the sum from I equal 1 to 4. But now in my function, everywhere I see an x, I replace the x with I plus 4 over 2. So I'm going to replace the x in x squared with I plus 4 all over 2, and that's squared, plus I'm going to replace the x here with I plus 4 over 2, so I plus 4 all over 2, and then minus the 4. Close off the parentheses here, and then we start simplifying. I get 1/2 times the sum from I equal 1 to 4. Parentheses, I need to square out the I plus 4. So if I square I plus 4, do I plus 4 times I plus 4, I'm going to get I squared plus 8I plus 4 times 4 is 16, and this will all be over. The denominator is 2. 2 squared is 4. Plus, here there's nothing that needs to be done, but I might want to, when I recognize that I have a 4 down here, I might want to multiply this by 2 over 2 to get a common denominator of 4. So that would give me, by distribution, 2 times I is 2I plus 2 times 4 is 8. Minus, and I may want to get a common denominator for my 4, so I might want to write that as 16 over 4, which is still equal to 4. And the reason for rewriting it with a common denominator would be to then identify that because the constant 4 shows up in all of the denominator positions, I can factor out 1/4, so I get 1/4 times 1/2 is 1/8 times the sum from I equal 1 to 4 of, and I factored out the denominators, so I just need to simplify the numerator term. So I'm going to get I squared, and then I'm going to get 8I plus 2I is plus 10I, and then I'm going to get 16 minus 16 plus 8. So 16 plus 8 minus 16 is just going to be 8. And now I have it in a form to which I can apply my summation formulas. We'll take one more little step here. This will be 1/8 times, I'm going to get the sum from I equals 1 to 4 of the I squared, plus, now I have a 10 times I, so it's going to be 10 times the constant times the sum from I equal 1 to 4 of just I. My 4s are worse today even than usual, and that should be a plus 8 sitting there. It was 16 minus 16 plus 8 is plus 8, so it's going to be plus the sum from I equal 1 to 4 of 8. And I'm going to bring this up on the screen so it doesn't get too low. So I have the area is approximated by the 1/8 right here times, and now I'm going to apply my summation formula. So the sum from I equal 1 to 4 of I squared, well, I have the sum of the I squareds. If n is equal to 4, I just plug 4 in everywhere I see an n in the summation formula, so I'm going to get 4 times 4 plus 1 is 5 times 2 times 4 plus 1 is 9, and it's all over the 6 in the summation formula, plus I have 10 times, and it's 10 times what? Well, this is the sum from I equal 1 to 4 of I, so the sum of the i's when n equals 4 is going to be 4 times 4 plus 1 is 5 all over the 2, plus, now I have the sum from I equal 1 to 4 of a constant 8, and when I have the sum from I equal 1 to n of a constant, I get the constant times n. So in this case, I'm going to get 8 times 4. And now it's just a matter of simplifying things. So I get 1/8 times 3 goes into 9 3 times, 3 goes into 6 twice, 2 goes into 2 once, and 2 goes into 4 twice. And 2 goes into 10 5 times. So we can simplify now. 2 times 5 is 10, times 3 is 30, plus, bringing down the plus from here, we get 5 times 4 is 20, and 20 times 5 is 100, plus 8 times 4 is 32. And now we just need to start adding things up. So we're going to get what? 162 in the numerator over 8, and it looks like for sure 2 goes into both evenly. So doing that, we're going to get 16 divided by 2 is 8, 2 divided by 2 is 1. We get 81 over 8 divided by 2 is 4, and that looks like it's in simplest form. So the area is approximated by 81/4. And again, that's an overestimate because in this case, each of the rectangles we used in the estimation process were above the curve, so we have an overestimate for the area under the curve.